So in a startup, I mean, there are these fancy words and fancy slogans that you've heard a lot about, but the interesting thing is working in a startup means to focus all your effort. And half of, for example, my work is just to think about where this focus should go into. So we have limited resources. We want to push really far. What can we do? And everything we do derives from the Xanadu mission. And you've heard it before, it's to build quantum computers that are useful and available to people everywhere. You can think of building quantum computers as hardware, being available, being maybe software, penny lane, people using it, and being useful. These will be the realms of Vanmige and myself and the teams that we're in, which is basically the quantum applications research teams. And so our vision for the quantum machine learning team is make quantum computers useful for machine learning. And this sounds like just, again, like business talk and very boring, and probably this is what everyone does. But it's very clearly not formulated in the way that many other teams formulate their goals. We do not seek to have a practical quantum advantage and show this as a business model. I'm very happy about this because otherwise I would probably not be here. That would be very dreadful. The basic assumption, so what we want is really to ask if in 5 or 10 years' time, quantum computers have an impact on machine learning, not just absolute artificial side subjects, but they actually like have a role, like a certain type of GPU or some supporting role for machine learning. What has to happen now in terms of research that this will happen one day? So we don't care about speed ups unless they are part of this path. And the assumption behind this is that we really need a completely different research agenda to get to this goal. And by research agenda, I mean really everything from what papers we write, why we write it, how we review them, how we speak about our goals, how critical we are about our own field. So that's kind of the bigger phrasing of this. And I basically want to convince you of what this research agenda is. I want to make a couple of comments that are important later. So I want to define machine learning. Many people think of it as training very, very big models with optimization methods that use gradients that have lots of parameters for models. This is kind of the paradigm of deep learning, and obviously this is dominating machine learning nowadays. But actually machine learning is something else, and I would say that quantum computing or quantum machine learning should not jump into this deep learning paradigm, but somewhere else. So machine learning is first and foremost the art of generalization. You've got a couple of data samples and you want to know how to generalize from them, how to sample from a similar distribution, or how to recognize patterns in this data. It's kind of like a very, very related task, actually. And so you can now, if you, for example, have the data samples on the left, they work or they suit to 2 patterns. And there are 2 ways to actually make your machine learning model kind of understand which patterns you're actually looking for. So for example, if you've got images, are you looking for cats and dogs, or are you looking for, is the image taken in the morning or in the evening? These are different patterns you kind of look for. And so the first one is the deep learning paradigm. You could add more data and make a model that could recognize everything. So you've got a model that can recognize smileys and circles, and you give a little bit more data, and then you hope that kind of it finds the things that it finds. But the other paradigm, which is a bit not, I would say the really, really old and very famous researchers in machine learning are also starting to walk in that direction again. So the second paradigm is make your model intelligent, use knowledge on the data. If you work in machine learning, you might have seen this very much in convolutional neural networks. Now people, convolutional neural networks were just like structures that were, or structures of neural networks that became famous for image recognition. And now all of a sudden people start finding the mathematical foundations of this and start realizing that they do have a very strong inductive bias, as you say. What does that mean? It means that these model classes favor models of a very specific kind. And this kind is a structure that's good for image recognition. So in short, what I would say is that the paradigm of kind of building intelligence, or you could say a bias into your model, is something where quantum machine learning could really excel at, but most people don't find that sexy enough, I don't know, but are not interested in this direction, because in machine learning, it's not a very big trend at the moment. So I would say we need quantum models that are, for example, circle classifiers. We have to understand what is the circle in the quantum case. What can quantum models really statistically classify? Second thoughts is, when you now have machine learning and then people started saying like, okay, maybe we need quantum computers, there are a couple of ways to argue. And maybe 99% of all people argue, okay, because they're exponentially faster, so we kind of like use them to speed up things. Highly related, but slightly different flavor is the idea that quantum mechanics has different statistical patterns. And I'm saying very clearly here, not quantum computing, but quantum mechanics, really. Like, think of Alice and Bob. Something statistically is going on there that's different. And you could hope that you can learn those patterns. And then obviously there's a big argument, usually summarized as quantum data. You can, like quantum simulations, people always have this idea, if we don't know what quantum computers are good for, we just say, okay, there are problems that have a quantum structure. So hopefully there we can do something. And maybe the one comment I want to make on this is that I believe we have to start investigating. So people started here on the left, and now they're going to the right. So this was like more classical data speeding up things. Now they're going to quantum data. I would say that the central part is very interesting. What are actually the statistical patterns we have got in quantum computers that make them circle classifiers, but we don't know what the structure is. Okay. So what happened in quantum machine learning before? How have people started bringing quantum into machine learning? The early papers, maybe starting probably in 2013. That's when I did my master's, I think, in the field. People have really thought about the patterns of how we do quantum computing, which means you take a classical algorithm, you see that the math suits an algorithm you can run on a quantum computer faster, so you outsource basically your computation. Does that mean the machine learning model would still spit out exactly the same results? You have just sped up the algorithm, the computation. So the quantum computer is basically a hardware accelerator, you can understand this. So if you know like all of these ideas with the QRAM and HHL algorithms for quantum machine learning, they go into that direction. Then maybe in 2018, like a lot of companies started jumping on the bandwagon of quantum machine learning, basically because they needed a business model for their quantum computers. I think they kind of NISQ era, and what people have done here is that they really like understand a quantum circuit as a quantum machine learning model. So basically the quantum circuit, the quantum algorithm is the pattern recognition mechanism. And this changes everything, because all of a sudden you're not just interested in, is there a matrix inversion in machine learning somewhere that I can outsource to a quantum computer? But you have to you have a completely different model class. You have to really analyze it. Is it good? What can it do? What changes here? So quantum machine learning looks basically at quantum circuits that are parameterized and now asks, how do they generalize? How do they train? How can we compare them to neural networks or kernel methods that are famous models in machine learning, and so on and so forth. But this is basically just to give you an idea of our work. I just highlighted a paper kind of every year since 2018. And one thing that's important to note is there's two tracks. I think at Xanadu, we have a very wide definition of quantum machine learning as anything that trains quantum models. Why? Because most of the methods that we use, for example, in Penny Lane, are inspired by machine learning software. So you can really say this is an intersection between the two fields. But there's also a stricter way where we say, okay, quantum circuits are machine learning models, and we also have a lot of work on this one. In the training quantum circuits, so the general variational circuits track, there was like this kind of like, there was a seminal paper by Mitterrand et al. Who proposed, it was basically just one sentence that said, oh, by the way, from control theory, we know that you can get a gradient out of a quantum circuit by just doing this kind of strange thing where you have two terms or something. And then it was basically Nathan, who's now our CTO, who looked at this and said, this is the basis of our software. And this is when we kind of tried to generalize it in this paper. And then this was when Penny Lane was born, basically. Penny Lane is based on this principle of what you know now as parameter shift rules. And our track in this research goes deeper and deeper into kind of how you can make these optimizers quantum aware. What does the structure of Hilbert spaces give you in terms of like power to understand the optimization process? In the other track, where we really ask what happens if quantum circuits are machine learning models that are trainable. So some of our work has looked into this idea of mathematically comparing these models that come out of this to kernel methods, which is it's a fantastic theoretical tool. So, for example, some of the first advantage papers in quantum machine learning use these methods to really do really great work. We have also looked into continuous variable and photonic quantum machine learning, but we stopped this for now because we're not building those devices anymore. I think there's a lot of interesting things to do there as well, but yeah, we abandoned it a bit. And we were quite interested in kind of embeddings, data embeddings, because we realized this is a really important part of the algorithm that people often ignore. Yeah. Okay, cool. Now to the part of where my kind of uneasy feelings started coming in. So I personally thought like maybe 2 or 3 years ago, whenever I see papers in quantum machine learning, I didn't want to read them. And I thought, what is happening with me? Am I just uninspired? But I started realizing that certain fields of classical machine learning, so I was still super inspired in the topic itself, but I just started realizing they always follow the same pattern. Something is wrong. We're all running into a direction where I don't think this is working. So I spent quite a lot of time with Nathan in last year to think about what are these doubts and put them, to some extent in this paper. I think the language is probably not yet crystal clear, but it's also in this blog post. I want to highlight a couple of these suspicions and problems. And I think a lot of this also applies to other quantum applications research fields that use VQE and variational circuits that they train. Okay, I want to explain those arguments in 3 patterns that we see in papers. The first pattern is introduce a quantum dropout convolutional neural net with feed-forward layers and recurrent LSTM mechanism or something like that. So what does it mean? People go to classical machine learning, make something quantum. I think the quantum convolutional neural networks are actually really the best example of this. There are lots of different proposals on how to do this, but no one asks why we need quantum. It's just the assumption that you add quantum to the whole mix, and then you just run your model, and then you benchmark it on a small data set and see if it's better. And the point here is that this should be obvious, right? But if you read through papers, I don't think this is obvious to everyone. Quantum is not better by default. Extremely impressive quantum circuits. So for example, you could make a quantum circuit of 1 million or 10,000 qubits, 1 billion parameters, can prove it's universal, can say it's maximally expressive, you can say it's classically intractable to a certain extent. But you encode your data in a certain way. For example, you encode your data input into Pauli X gates in a certain way. You can make a machine learning model that's just a sine function, and all your 10,000 or your 1 billion parameters are just there to tune the width and the amplitude of the sine function. So this is known. You can write this down how this works, and but I think it's not taken serious in some sense. So I do think we have to be very careful when we port over concepts from classical machine learning. And I'm also probably the only one in the field who hates the term quantum neural network, although I use it sometimes myself because by now it really describes something that helps us to communicate to each other. But a quantum circuit has nothing of a neural network, and it shouldn't have. There's something else in the quantum circuit that's interesting. I don't think it is just to turn activation functions into quantum properties. The second pattern is that we always see is obviously the good old quantum theory, like we prove an exponential speed up for this QML model. And there someone really has to explain to me the following point. Again, our goal here is not, I'm not talking about the academic efforts to understand like very kind of very specific regimes and artificial regimes, or if something exists or something like that. I'm really talking about making quantum computers useful for machine learning. So here, the point is that every machine learning algorithm that you can download and pip install today runs in linear time in the size of the data. If not, I mean, this was the graveyard of kernel methods, and which is why people introduce things like random Fourier features or something like that. And especially in neural networks, and including the entire training mechanism, run linear in the data size. Or you could say, okay, quantum computers speed something up exponentially. And quadratic speedups are quite out of fashion, as you might know, because people say, okay, error correction is such an overhead, we really need like a real boost by quantum computers. So if you now say like we can go sublinear, that means I don't even load every data point once. So a sublinear quantum machine learning algorithm means I don't even load my data and look at every data point once. So there's no way I can take all the information out of my data set. And if I don't take all of the information out of my data set, maybe I compress it or I load it into a compressed format, I have to compare to classical algorithms that also like are sloppy. So this is like kind of something where I'm very, very confused why. I would say that the way we measure speedups using computational complexity language has no room in machine learning. And this is why, for me, machine learning is actually an application that's super interesting, because you can kick quantum computing out of the methods that they used for 30 years because there was no other way of describing things. But I think slowly we should go into a language that also looks for other things. And we should not only write papers and like papers that use this language. People can do this, but not everyone should do it, I think. The third pattern that I see a lot is like, just people actually like make a model, propose a model, there's often like some nice quality about it, then they close their eyes, take something like MNIST or a data set that classical people benchmark their models with and just say, this is like my quantum model and how it performs. And if you go through these papers, almost all of them say, oh, the performance is good and the performance is better than some classical model or in the same region. And I mean, this sounds almost too good to be true. I suspect, and we're doing a bit of research in that direction to make this more concrete, I suspect there are two problems here. I do believe there's a huge positivity bias, and this is why I say we don't only need a change of research agenda direction technically, but we also need a change of culture in quantum machine learning and in quantum applications. Because if everyone runs 100 experiments and only reports on the best one, guess what? These are all the experiments you ran, and these are the ones you report and that we see in the papers. There's something really like going wrong here. And there was actually in, I think the field of social psychology had, I think it was 10 years ago, someone kind of suspected a positivity bias. They did a huge meta study and realized that hardly any study is reproducible, and they changed their methods entirely. I read up on it like in some article. It was super interesting. And so we should be really careful, right, with how our methodology works if we report on good results, because there's a bias towards good results. The second problem is that at the moment we don't test at scale, so we test only very small problems. So if you use MNIST, everyone always downsamples it with PCA methods and so on and so forth. And a lot gets lost in what happens in the bigger regimes. So the regimes in which machine learning nowadays is working and is interesting is not the regimes that we test at the moment. And there's a suspicion, so this is totally unclear because we haven't looked at this yet, but there are a couple of hints that the scaling won't be as good as we hope. So one of the examples is the trainability, like the scaling of our training doesn't scale to huge parameters. The idea of barren plateaus, we're also a bit skeptical about, but also there. So things are not as rosy if we scale up. So we need these investigations that push higher. And so our objectives for this year are to identify, boost and contribute key ideas which will accelerate quantum machine learning research. Again, this is business talk, but what we really mean by this is that we are a team that searches for the ideas. We also search within us, but in the literature for these key points where we think this is the beginning of a new direction where we leave where we are at the moment. And I think, so 2 concrete projects we're working on at the moment, and in the meantime, until we find the great result, is the first one is basically to make a bit more explicit, because I can always claim, okay, our models don't scale, there's a positivity bias and so on and so forth. But we can actually test this. So we go through the literature and do a meta study. We spent literally the last couple of weeks in a team looking through all quantum machine learning papers that tested data on MNIST and just try to see like, what are they doing? How many qubits do they use? Like how's their reporting and so on and so forth. And we want to know how good are quantum models really that people propose. So there's a lot of like this sounds very boring reproduction work, but if you go down to the nitty gritty, it's a very different way of science. So it's maybe not the science where you sit and calculate a lot and prove things. I think lots of us really like this type of theoretical or very technical work, but it's a science where you have to look into your methodology. So it's really the heart of science that you test here. Which benchmark data set do we use to reproduce those results? Like, how do we choose this? So you have to really go back to the basics of what do we want to probe and define your scope and so on and so forth. And then the research team also feeds a bit into penny lane development. And I think the bigger vision is, now everyone tests their models on MNIST or IRIS or all these data sets that 20 years ago people have done in classical machine learning. So if we start criticizing them, there is a need for a method of how to check how good your model is. And this applies to all quantum applications, also for quantum chemistry that you will learn about tomorrow. It's really like, how can we create software, create maybe certain leaderboard competitions? How can we create frameworks that a student who's a PhD student who has got a cool idea can just within a couple of weeks verify this model is working or not? Very unclear how this works. And then one project that that I'm working on quite a lot these days is to kind of like reassess why we need quantum. This goes back into this idea, what are actually the statistical patterns we use? Might see a couple of papers that are a bit more experimental and going into the foundations, like what do we learn from Alice and Bob? How can we turn the language of quantum foundations into a machine learning framework? Not sure if this leads to crazy insights yet. I would hope that other people would push this as well a little bit more. So we go back to quantum computing at the moment, and we really look into what are the engines behind Schuld's algorithm, like Fourier sampling. Like lots of quantum algorithms go into a basis done by the quantum Fourier transform or by Hadamard transforms, and then sample in the computational basis, like after this transform, and reveal information. So this is a way of revealing statistical information about your problem. How can we bake this into a machine learning algorithm? And sounds maybe not crazily different, but the big difference is that you could do this just like take Schuld's algorithm, put some variational parameters, and then learn something. But we want to go a completely different route. We want to kind of make the quantum algorithms less precise, less rigorous. We want to lose the ability to prove anything, but we want to capture the ability to do something. If any one of you knows what I'm talking about, for example, quantum algorithms there's no algorithm known yet for a problem like graph or isomorphism. So what would a typical quantum machine learning researcher do? Would say, oh, graph isomorphism is nothing that we can do a speed up, so it's not interesting for us. I say maybe it is interesting for us because maybe quantum computers can't solve graph isomorphism, but maybe they can bias a model class into the direction of graph isomorphism more than another model could. Instead of being a circle classifier, it could be, it knows things about graphs better or faster than classical models. That's this idea.